on Monday, we talked about equilibrium of a rigid body. And we said that for rigid bodies, in addition to considering your force components, in order for a body to be in equilibrium, we also have to consider any rotation in that body. Which means that if a force is acting on a body and is causing a rotation about a point, I thought this would be easier, is causing a rotation about a point, then another force has to counteract that rotation. Pick the wrong thing to try to rotate. But you get my point, right? Rotation, rotation. So in addition to x forces canceling each other out, y forces canceling each other out, z forces canceling each other out, we also need moments, that is rotations, to cancel each other out. So when we study rigid bodies, we're going to find the next, or we're going to find the best way, I would say, to apply these equations. And what we're going to see that we find ourselves doing is we're going to try to look at particles or at bodies as if they were particles, but considering directions. Now I'm saying a lot of different words: bodies, particles, directions, and so on and so forth. I think the best way to explain this is through a problem. So let's go ahead and work on example 5.5 from your book. And in this example, we have a beam. And this beam is supported, okay, is supported by a hinge and a roller. Okay. So this little beam is supported by a hinge and a roller. You'll notice that your book draws rollers in this fashion. When I took statics, I'm used to drawing rollers like this. But they mean the same thing, right? Free movement laterally, right? But then a reaction force normal to the surface. Now, who did watch Monday's video? Riley? Okay. What does this hinge do for this beam?
It controls like linear forces up and down.
Yep.
Side to side, up and down.
That's correct. Leslie, can I rotate this beam freely around this hinge?
Yes.
Yes, I can, right? Because hinges prevent linear translation, that is linear movement, but they don't prevent rotation, which means that I can rotate freely around the hinge. Rollers, they also don't prevent rotation, and they only really create a reaction normal to the surface they're in. So if this is a horizontal surface, my reaction will be perpendicular to it, so it's a vertical. Okay? So rollers, only one reaction, normal to the surface, but free movement laterally. Hinges, no free movement laterally, no free movement vertically, but free rotation. We're going to talk more about these types of supports, but for now, we focus on these two, hinges and rollers. I'm going to write it down, hinge and roller. In the future, I'm not going to write all of them down, but I just want you to get used to how these two look. Let's say that we have a couple of forces acting on this beam. We're going to start with a 200 Newton force at one end of the beam where the hinge is, a 600 Newton force at an angle of 45 degrees. And here's where we want to be careful. Let's say that the distance between the center line of this beam, let's say that the center line is where the roller and the hinge are connected. The distance between this center line and the top of the beam is 0.2 meters. That is 20 centimeters. Okay, so that's the distance between the center line of the beam and the top of the beam. We have a final force that is applied of 100 newtons. And we are told to neglect the weight. Okay, so I'm just going to write it down, neglect the weight of the beam. Okay, so we have the system. Now, I would like to ask, if I ask you to solve this system, what I mean is that I want you to find all of the forces acting on the system. That's when I say solve the system, I want all the forces in the system. But then my question is, what is the system? If you look at this diagram that I have just drawn, and I ask you to tell me what the system is, what do you think the system is? Think of when we're looking at particles. When we looked at particles, we always had to pick one point where to draw the free body diagram.
Are we going on a hinge?
Sorry?
On a hinge?
Well, in this case, see, in this case, we're not picking one point. In this case, our system can be a whole body, right? So what do you think that body will be? What do you think most forces right now are acting on? Our beam, right? So in this case, our beam is the system. And that's how this procedure differs from chapter 3, because in this procedure, we are looking at an entire body, not just a point in the body. So I have discovered my system. Once I know what the system is, what's the very first step I always mention we should do? Free body diagram. Good. So we're going to draw a free body diagram, and this time it'll be a free body diagram of the beam itself. Now, before we start with this free body diagram, let me give you some distances, and we'll learn why we need those distances in a second. Let's say that from the roller to the application of the 600 Newton force, we have a distance of 2 meters. We have a distance of 3 meters from that force to my 100 Newton force, and then 2 meters from that 100 Newton force to the hinge. Now, when we draw free body diagrams, I mentioned that in order for me to say that this is a good free body diagram, I should be able to solve this problem without having to look at the diagram. So that means that this free body diagram has to include everything I need to solve my system. So free body diagram, of course, we draw our body, we isolate it from the system, and then we apply all of our forces acting on it. So what forces do you see here? We're neglecting the weight, so we don't have to worry about the weight of the beam. But what forces do you see here, Will?
200 Newton force.
Okay, we have a 200 Newton force. Okay. We have a 200 Newton force. I'm just going to simplify this and say that this is the end of the beam. This is the start of the beam, just to ignore this extra side. So I'm just going to say 200 Newton force at the end of the beam. What other forces do we see here?
The 100 pulling down from the bottom.
Okay, we have a 100 force pulling down. Okay. Newton force. What else, Lorenzo?
We have a normal force on the roller.
Let's leave the reactions to the end. Let's just look at the impact forces right now.
Then we have the 600 Newton force.
Mm-hmm.
45 degrees, 2 meters.
I like that you said all that, right? Because we don't just need the magnitude and direction of the force, right? We need the location of the force. Now, in last class I mentioned, your location should be relative to something. And typically we say that the location is relative to an origin. Now, where you place the origin is up to you. And as long as you are consistent with your measurements, it doesn't really matter where you place your origin. But I prefer to place my origin at a point where I have forces acting on it. So at a point where the location is easy for me to find. So here, I would like to place my origin at the left side of the beam. Okay? So if this is my origin, we know that this 600 Newton force is acting at a horizontal distance, right, of 2 meters from my origin. We know that this 100 Newton force is acting at 3 meters from my origin. We know that this 200 Newton force is acting at 2 meters from my origin. That means that this beam is 7 meters long. Okay? So we've identified these forces. And now let's go to the reactions. Now we know that this system, even though we are drawing it as if it were isolated from an environment, it's actually not isolated from the environment. And we know that in standard engineering conditions, nothing really is isolated from the environment. Everything experiences some sort of force from your environment. Even right now, in addition to gravity, which is, I guess, a body force, you are experiencing forces from your environment. You're experiencing a normal force pushing you upwards. You're experiencing atmospheric pressure pushing down on you, right? So because we are trying to draw this beam as independent from the environment, we need to look at the effects of the environment as if they were forces, or in terms of forces. So in this case, what are the effects of the environment? What forces is the environment, or are the environment exerting on the beam?
So the roller is pushing up on the left side.
Okay, the roller is pushing up on my left side.
An unknown amount.
I'm just going to call this, I think the book gives this point A, so I'm just going to call this RA. And can you say the other one?
So then the hinge
Mhm.
is also holding it up,
Okay.
but it's also going to be holding it in the X direction as well.
Okay. And this is just a guess. Well, you can figure it out, but it doesn't matter if you get this wrong, but in which direction should I draw my X reaction? What do you think?
This way.
Towards the left? Okay.
You
And
have
again,
to be
it-
finding the 600 Newton.
Exactly. And it doesn't matter if you get this wrong, right? If you chose the wrong direction, you'll just get a negative sign in your answer. But yeah, right now, these are my reactions. These dark arrows are my reactions. And we have my forces. And we don't know our reactions, at least not yet. Okay? So now, let's go ahead and solve this system. When you have a system, you draw a free body diagram. This is a static system, a system in equilibrium. So you turn to the fundamental equations of this class. Everything has to equal 0, okay? So how do you want to start this? F of x, okay. So we get that my sum of forces in the x direction equal 0. So what do I have in my x direction?
You're going to have the 600 newtons at a 45-degree angle, which should be, what, 300 newtons?
Nope. Just give me the trick behind it, right? Cosine 45, right?
Yeah.
Of course, in this case, sine 45, cosine 45, they're the same thing. But let's try to be consistent, right? Cosine of 45, because we're looking at this x component. Okay, what else?
RBX
Plus or minus?
minus.
Minus, right? We drew it towards the left, so I'll just write minus. And all this equals 0. This tells me, right? This tells me that my reaction force R B x equals 600 times cosine of 45 degrees, which is,
424.26.
sorry?
424.26 newtons.
424.26 newtons. Good. We found one reaction force. We found that this force is 424.26 newtons. Any questions up to this point in this problem? If this were the oral exam and I say, solve this example for me, could you get at least to this? What? You can now. Okay, good. Tyler, I like your optimism. What's next?
Start with F and Y.
Okay, so let's go with f of y. And remember, there's no order of steps that you have to take. Well, this goes first. But other than this, there's no order of steps that you have to take. Sometimes you'll find that your equations can be solved easily. Sometimes you'll need to skip and go to the next one, and that's okay. You just solve whatever you can. So f of y. What forces do I see in the y direction, Tyler?
600 newtons times sine 45.
Positive or negative?
Negative.
Okay.
And then minus 200
Chris, what forces do you see? Original Chris.
The negative 200,
It's already there.
negative 100,
Other Chris?
RA and RB1.
Positive? Negative?
Both positive.
All this equals what, Kevin? No, just right now, this equation. Don't. Okay, there we go, 0. I don't know why. This entire week, I always ask my students, it equals what? And everybody just starts to calculate. I'm like, just say 0, right? That's the answer. Everything equals 0. This is statics. How many unknowns do I have in this equation? Ooh. So is this equation enough to solve? Ooh, we need another one. Leslie, where do I turn to? So you started solving this problem. You realize that you can't solve for RA and RB using just the FY equation. Where do you go to now?
So the sum of the moment equals 0.
Okay. And here, remember, sum of moments at any point in this beam has to equal 0. So you can pick whatever point you want. Sometimes you may actually have to pick more than one point. It's important to pick the right point, okay? Because sometimes, let's say I pick a point here, and I want my moment about the center of the beam to equal 0. How many unknowns am I going to end up with? 1, 2. So it doesn't help me. So where do you think you want to pick your point? My advice, and I've said this on Monday, I'm going to say it again today, and I'll probably keep saying it for the next couple of days. My advice is to pick your point somewhere where you can eliminate as many forces as possible.
You're going to put it at point RB.
Exactly, right? You want my moment to be here? Because notice that here, we're already eliminating this RB. Okay? We're eliminating this RB. We don't even have to consider this Rx because they both pass through the point. Now, if you don't understand that, think. Moment is force times distance. Yes?
Can we also eliminate 200 at this point?
Yes.
Because it's in line as well.
That's correct. Moment is force times distance, right? So what's the distance between this force and this point? 0. So there's no moment. So we pick a point that has the most forces, specifically the most unknowns attached to it, so that we can simplify our equation. Because now look at this. I pick my moment around point B. And what forces do I have? I have RB, but that's a moment of 0. I have RBX, but that's a moment of 0. I have a 200 Newton force, but that's a moment of 0. So picking this point actually leaves me with only 1, 2, 3 forces. And if we want to be more specific, right, breaking into components, 1, 2, 3, 4 forces. So it's actually very helpful. So I'm going to draw my Y component here. And let's go ahead and find our moments. I actually realized something. Looking at this free body diagram, we forgot one distance here. Can you see it? What distance did I forget, Riley?
The distance from the middle of the beam.
Yep. From the center of the beam, 0.2 meters or 20 centimeters, okay? Very important that we caught this, right? Because again, I should be able to solve this problem without looking back at the diagram, okay? So, let's go ahead and find our moments. Sum of moments equals 0. Lorenzo, why don't you start? We're looking at moments about this point.
We could do 100 times 2 meters.
And would that be a positive or a negative moment? Okay, we got a counterclockwise rotation, positive moment. Chris?
RA times 7 meters.
And would that be a positive moment or a negative moment?
Negative.
Chris?
The 600 sine 45 times 5 meters.
And would that be positive or negative?
Positive.
Will? considered the 100 Newton force that's making a rotation about this point. Right? I don't have to consider these three because they all go to 0. I consider my RA. I consider my vertical component. Is there anything else that I need to consider? Remember, any force that acts at a distance from this point will cause a rotation. So what other forces do I have acting at a distance from that point?
The X
Go ahead.
component of the 600.
Exactly. Remember, this x component acts at a distance of 0.2 meters. So it doesn't matter how small that distance is, it's still there. So we have 600 cosine of 45 times what? 0.2. Good. And will that be a positive moment or a negative moment? Okay. Notice that this is a clockwise rotation. Is it above the point towards the right? That's a clockwise rotation. Let's try again. Kevin, all this equals what?
Equal to 0.
There we go. Good. Now how many unknowns do I have? Just one. So now can we solve this? Yes, we can. So let's go ahead and solve this. We get that RA equals what? I wish I had some incentive other than bonus points to get you to solve things quickly for me. But I don't know what else to give. And I don't just want to throw out bonus points all the time. I know. Whoever solves this will get my respect. There we go. So what is RA equal to?
100, 200.
I thought 319.5.
Can somebody confirm her number? Yeah?
Yeah.
Okay. So we got 319.5. Or just 319 or 320, depending on how you want to round it. And did we assume this direction correctly, Leslie? Did we assume that RA goes upwards, and is that correct?
Yes.
Yeah. Of course, with rollers, it's easy, because with rollers, this is the only direction that your reaction can go. But if it were a hinge, hinges can also provide reactions in the negative direction. So we found our RA. And now, can we go back to this equation and solve it, Tyler? Okay, so let's go ahead and solve it. We know that RA is now 320 newtons. So RB equals what? And I want Tyler to solve this one. Can somebody confirm this number? Okay. Good job. I always prefer that you box your answers, but I don't want to waste so much marker ink. But yeah, we solved this system. And by solve, I mean we found all the forces acting on it. Any questions? This is essentially the crux of chapter 5. So any questions with this system? No?
So with the x component of 600 newtons, it's 0.2 meters, but why is that in there again?
So remember that moment is any force that acts at a distance, right? So we have this line of action, the straight line, right? A line of action of this force. And you want the closest distance or the perpendicular distance between your point and the line of action. And that perpendicular distance, notice that is 0.2. Okay? The reason I choose my point at the center is so that it intersects with this RBX and we can take it out of the equation.
Yeah.
I could have easily chosen my point up here, but then I would have had to consider my RBX. You have a question?
No.
Okay. All right. Any other questions? I know this is, it doesn't seem like it, but this is the heart of chapter 5, really. If we understand this, we should be able to move on to more complex problems. So before we move on to more complex problems, are there any questions? Okay. Let's do something. Just because I want to do something interesting. How about the next problem? I'll draw it, and I won't guide you. You will tell me what to write. And I won't say if it's right or wrong. It's up to you to determine if it's right or wrong. I think this will make the class a little bit more fun for me and a little bit more useful for all of you. Consider this a practice oral exam, okay? Because that's essentially what it's going to be, what the exam is going to be like, okay? So let's say that I want to solve the following system. And because it's a practice exam, I will allow no cheat sheet. So that means that you're going to have to memorize these equations. Ooh, I erased the equations. Now how will we solve this problem? Yeah. All right. Here's an interesting one. Remember we talked a little bit about reduction of forces last time, or last week or the week before, so we're going to have to look into this, okay? So we have example 5.7. And here we have a rigid body that is connected to a pin. So I'm going to try my best to draw this rigid body, but for your reference, it is in your book, example 5.7, page 224. So I have my hinge. Remember that hinges are sometimes called pins. And this is connected to something else. It says the member shown in the figure is pin connected at A. I'm just going to call this A if it helps you. And rests against a smooth support at B. So this is a smooth support. What kind of support do you think this is? What will we call this? Where do you think the reaction is? It's like a roller, right? Only a normal reaction. Good. I'm glad that you know this. That's the last. I'm not going to guide you so much. Just wanted to make sure you know. We have a load, not a force, a load of 80 newtons per meters that has a triangular shape. So it has a maximum of 80 newtons per meters, and it has a triangular shape. We have a moment that is a rotation of 90 newtons times meters. We know that this member is inclined at 30 degrees. And we know that this member has a length of 0.75 meters. And this member has a length of 1.5 meters. So given all this information, I would like for you to solve this system. Begin.
As a class?
I guess we can do it in order so everybody gets a chance to participate. Let's start with Leslie and then just move.
I need to draw a free body diagram first.
How do I do that?
We have to draw the system, which would be the, oh god.
The God?
No.
I'm not sure if I'm even allowed to draw that. So
Is that like a, what is it like a beam of sorts? Like,
yeah, let's just call it a thing.
Okay.
Okay.
So you draw that shape.
Okay.
two will only have the moment and the X part of B. It'll actually,
You're getting a little bit too ahead of me, okay? What now? Just right now. Like, I'm doing this, I'm solving this problem. What do I have to do now?
so at point B,
Mhm.
we have to put our force in the X direction and the Y direction.
Okay. I know that it's in this direction right now. So like I said, you're getting a little bit too ahead of me. I'm going to break it into components later, okay? What's this force called?
F of B.
Can we just call
F
it B?
of B.
Agree. You need to agree on something.
You can.
It doesn't matter.
Okay. Do F of B.
Okay. We need to agree here, okay? Again, I know nothing. I am like you. Well, back in August. Tyler, your turn. Tyler, is this the only force that I have to draw?
No, I'll just pick even first. We can go with the moment, I guess.
Kevin?
From the point of the FB, the 30 degrees to the like the top, and the top of the FB. Yeah, right here to the top, and then there's the 30 degree.
Where?
It's like the straight up,
Like this?
kind of. Yeah.
Does everybody agree? Riley, your turn. Do you agree with him?
Yeah.
Okay. So, what's next, Riley?
We have a reaction force at A. So, you can do like FAY and then AX. Yes. Pointing up. Not sure what direction that one should go.
Right side. FAS.
Yeah, FAS.
Let's go with Chris.
Should we put the load on there?
This is not wrong, but sometimes free body diagrams, we like to reduce everything to forces. Is that something that you think you can do for me?
Probably.
Okay.
Okay, so the force for the load would be um, 80 or 1/2 times 80 times 1.5
Don't forget your units.
newtons.
Comes out to 60.
Newtons.
Lorenzo, what now?
Now, I'm not sure.
Chris?
Do we just put one arrow in, like on the original? Can we put it on the end? Like where the dot is? No?
Here?
Uh,
Leslie?
I think so. I think that's where you put
I
it.
know we can, I just don't know which one's easier. Easiest.
2/3 of what?
So 2/3 from the left side of the 1.5 meters.
Okay. So where then is it located?
Um, yeah, should have done that. Okay. 1 meter to the right.
Good, good, good. Before we start actually solving this problem, I'm missing something.
The 0.75 meters.
There we go.
And we probably need the meters to the end of the other place, which is half a meter.
Will, is this a good free body diagram? Let's say you're the teacher. You're grading this free body diagram. What grade would you give this free body diagram?
You have all the forces on it, and you can solve it without looking back to the original problem. I'd give it a 1. Or maybe 2 times.
You're too kind. I would never give 100. But it's okay. I respect you. Leslie, let's start solving this problem. Uh-oh. I erased your equations.
No.
Whatever will you do?
So forces in the x direction equals 0.
Let's do a bit of a free-for-all. If you know what I should write, just
Can I split my b into 2 now?
yes.
So we have the x value of b and the y value of b. And in the x direction, we're going to have a negative f b of x.
Plus a of x.
That should be it.
Equals 0, yeah.
So f of bx equals f of ax.
Recommendation, try to reduce the number of variables. So since these two, f of bx and f of by, are actually related to one variable, f of b, let's express everything in terms of that one variable, f of b. So instead of f of bx, what could we write?
f of b sine of 30.
Now we gotta move on to sum of forces in the y direction. So the first one would be our L equals 0. We've got negative 60 newtons. Minus FB cosine 30.
Plus our f ay. Equals 0.
We change y to cosine 30? No. Yeah. No? Oh, never mind. Okay, got it.
Now we need some moments equals 0.
Where? What's your point?
Um,
Like, what's the point at which you want to find the sum of moments?
probably like a. So we have a 90 newton meter moment in the negative direction.
Plus FB times 0.75 meters.
FB times what?
0.75.
Is the 90 newton meter moment on a certain point in the body?
It doesn't matter. it's just a rotation. It doesn't matter where I'm exerting it. It will apply equally to any point in the body.
And then we have our 60 newtons. It'll be negative times our 1 meter. We can actually solve for this one. To simplify, so to simplify, we have negative 90 minus 60 divided by 0.75 equals FD. It'll all be positive. So 90 plus 60 divided by 0.75.
This may seem redundant, but I encourage us to always write down our units. We may not need it now, but in the future we will need to understand why we're canceling things. But other than that, you're good. Correct me if I'm wrong. I just want to try to participate. Ooh. Correct me if I'm wrong. I'm very wrong. You got like 2 steps left. Hunter, you're talking too much. And that's really good. You participate too much. And that's really good.
I have a question.
Oh, yeah, go
In
ahead.
this case, why is it okay that we have 2 meters on the top and only 1 on the bottom when we end up with newtons?
This?
Oh, because you're adding on the top, you're
Yeah.
not multiplying. It's
Oh,
not
so it was,
squared.
okay.
This is just the same as 90 newtons meter over 0.75 meters plus 60 newtons times 1 meter over 0.75 meters. It's the same thing. Okay? All right. I love that you two are participating so much. Lorenzo, I'll let you finish this problem.
I go back to f of y, plug in the value for fb.
Okay?
And then you get that it's 232.
What? 200 what?
33.3.
Okay. Original Chris, wrap up this problem for me, please.
You plug the 200 newtons back into the f of b for the x.
Is that right?
That's right, yeah.
Okay. Will, are we done?
Yes,
Have we solved this system?
we have.
Do you do it with minimal intervention from my part? Yes, for the most part. Good job, everyone. It'll be like that, but you have to do 2 of these in 15 minutes. So kind of like that. Good job.
Are they all this complex though?
Yeah. I mean, first of all, I'm not going to give room for empty spaces, right? So I'll be like, hey, give me the answer. If you don't give it to me, I'm going to force someone else to answer, right? But the idea is that you're going to walk me through your problem as if I didn't know how to solve it, and you're explaining to me how. So think of it like you're tutoring me, and you're explaining to me how to solve it, and I'll grade you based on how well you explain it. Yep.
Would we be allowed to write down?
You're,
Board or paper?
Yeah, and there'll be problems that you already did for your homework, so you'll have your homework with you. So you actually will have the solution. You have to explain to me how you got to that solution, assuming that you actually solved your own homework,
How
right?
are the groups learning?
What?
Aren't we in like groups?
Yeah,
There's
so,
like 4 of them.
Like 5?
yeah, individual grades though, so
like,
you'll,
what if one person is talking a lot? Are you gonna like?
no, I'm not gonna allow that. So
stop and
I'm
then-
gonna tell I'm not gonna let people answer on their own. I'm actually gonna address specific questions to each and one of you. And then I'm gonna ask you to start the problem, and at some point I'll say, okay, Hunter, what's next?
Okay.
So I'm not gonna, yeah, I'm planning, on that.
Okay.
Because if we have a group right now, Hunter and you would actually kind of like answer everything, right? So I need to make sure that everybody else gets a chance to participate. Oh, can I erase, I guess? Yeah. Okay. Yeah, I kind of erase without even asking. Yes?
Oh, I had a question, but it's not going to topic. Can you explain the 2/3 thing?
Yeah. So we have this load, right?
Okay.
It's triangular load. So we've reduced it into a force because we know this load is acting over a distance of x, okay? It has a maximum value of, I'm just going to call it P. And we said that the force is equal to the area that this triangle forms. So the area of a triangle is 1/2 base times height. And that's what we did, right? 1/2, 1.5 times 80. Good. But now let's look at where that force acts on. So the force acts on, we said, on the centroid of this distribution. And this centroid, right, is the geometric center of your shape. Think of it this way. If you were to balance this triangle on your finger, would you balance it on the center? No, because you'll have more weight on one side. So where is that balance point? At 2/3.
Okay, so that's just for triangles, though, right?
That's just for triangles, right? So this would be 2/3 of x. 1/3 if you're measuring from the big side. And since you asked, let's review. What's the force here?
1/2 x times, or x times 8.
There we go. And where am I going to balance this force?
Half x over 2. Or,
Yep, yeah, you're good.
okay.
Does that make sense? Yeah.
So what if you had a different like angle though? Like let's say the triangle's like super tall on one side, would you balance it more towards the right side, for instance? So would
What do you mean, like
Yeah, so would that be still 2/3 more?
like this?
Yeah.
2/3.
It would be because you're gonna end up with the same amount of weight on the first 2/3.
Yeah. Then on the last 1/3. Yeah, it's always any triangle. Doesn't matter. It's always 2/3.
If you ended up with like an equilateral triangle, then it would be right in the middle, right?
Yeah, but then where is that middle? At 2/3 from the top vertex, 2/3 from the left vertex, 2/3 from the right vertex. It's always 2/3 for triangles. I will.
Like for our calculations, it would be the middle. Like one, and then, like whatever our bottom distance is, it would be half that.
Oh, if it's like this, then yes, yes. If it were like this, yes. But if the triangle were something like, here's where it gets more complicated. It's not an equilateral triangle, but it's not a right triangle either, right? So what do you think the centroid is here? Becomes hard, right? So
it's 2/3 from all of our corners.
well, here's the thing. When you have a complex shape, and I'm gonna let me find a complex shape problem to solve. But when you have a complex shape, the best thing to do is, let's say I have something like this. Instead of trying to find one force and the location, it's okay to break this down into two segments, a rectangle and a triangle, each with its own force, each in its own location. So if I were to have a triangle that's not equilateral, it's probably better to break it down into two triangles, each with its own force and each at 2/3 from the small side. Okay? So, good question. I'm glad you brought it up. Let me go ahead and look for a problem that has something like that, because that'd be a good exercise for us. Yada.
Most of the time, we could probably split it into triangles and squares or rectangles, right?
For this class, yes. Right? In future classes, no. So,
When we get into like hard calculus and all
yeah,
that.
integrating, all that stuff. Okay? Let's do example 4.23. We have a trapezoidal load. What was I gonna say? I have I don't have the proof. I don't know the proof right now, but I teach a geometry class, and well, we went online, so I don't teach it anymore. But back then, last year, I used to teach a geometry class, and it's they market it as a school for high performance learners. So what that means is like these geniuses. And in that geometry class, we make a lot of proofs. And one of those proofs is why the centroid is always at 2/3 in any triangle, no matter where. So at some point, let me look up my notes, and I may actually show it to you, just so that you have some bit of a strong geometry background. Because I love that class. I wish I could still teach it, but since we're online, I don't teach it anymore. But it's a very fun, very rigorous geometry class. I mean, even I don't understand what I'm teaching. I'm like, whoa, how do these guys understand it? But anyway, let's do problem 4.23. And because this is from a previous chapter, they're not asking us in the book for the reactions. But you know how to calculate reactions as well. So we're going to make this problem a little bit more complex because we know how to solve the system. So take notes, because in the book, you're not asked to solve this system, but I would like for you to solve it. Okay? So we have a beam with a distributed loading that has a trapezoidal shape. Let's say it's all the way to the end. We have a minimum load of 50 pounds per foot, maximum load of 100 pounds per foot. And the beam has a length of 9 feet. I think that's all the information we need. The beam is supported at a fixed support. Now, what does fixed support mean, Riley?
That means that it controls both lateral movement and moment.
And moment, right? So we cannot rotate this beam freely, right? The fixed support will prevent it from rotating. So now let's solve the system. What was the first step? Okay. This actually looks good enough to be a free body diagram. There we go, free body diagram. What forces do I have? What forces do I need? Will?
The 100-pound foot on the left side, 50-pound foot on the right side.
These are not forces, these are loads, as you can see.
Yes.
Leslie, help him out. This is a trapezoidal load. Now, there's two ways we can approach this. You can find the area of this trapezoid, but it's actually quite easy, right? Average of 50 plus 100, so 50 plus 100 over 2 multiplied by 9. Or, there's another way we could solve this. What's the other way?
Cut the triangle off the top of the rectangle.
Okay, so break this down into a triangle and a rectangle. Good. So I'm going to break this down. This 50 and 100. I'm going to break it down to a triangle and a rectangle. What's the magnitude of this rectangle? What's the magnitude of the load of this rectangle? Okay. What's the magnitude of the load of this triangle? That's correct. Why not 100?
Because we're not taking half the...
Exactly. 100 would be everything including the rectangle. Does that make sense, Tyler? It's okay if it doesn't. That's what we're here for in this class. We have a 50-pound load. That means that from here to here, we have 50. From here to here, we have 100. But the triangle really only includes this part, right? So we have a load of 50. The whole thing is 100, but the triangle, notice that we're only cutting out the top part.
So I should think about it less in terms of like which is on the right and left, and more about the height of where they put the force.
Yep. So this is 100 minus 50, or just 50. Okay? And of course, this is just 0, because that's where our triangle starts. Okay? Good. So we've broken down this trapezoidal load into two loads, a triangular one and a rectangular one. So what are the forces of these loads? We got 9 foot on both, right? 9 foot. 9 feet, not foot, feet. So I'm just going to call this F1, F2. What's F1? You don't have to give me the final number. Just tell me how to solve it.
1/2 times 50 times 9.
Units. 50
no.
pounds per foot
Yeah.
times 9
9
feet.
Yeah.
How much is that?
225.
Sorry?
225.
Units.
Pounds.
Where does F1 act? If we're taking an origin at the left, where does F1 act?
3 feet on the left.
Why 3 feet?
Because it's the 2/3 rule, but we're triangles facing in the direction, so.
So it would be,
1/3 from the left.
there we go, 1/3 of 9 feet, which is 3 feet, right? Okay, good. So we have our first force. We have a force of 225 pounds acting at a distance of 3 feet. How about that second force? What is that second force equal to? Again, don't give me the final number, just tell me how to solve it. How much is that? And where does it act on?
1/2 times 9 feet.
And how much is that?
4.5 feet.
Okay. Good job. Are these all my forces in the system, Will?
Yes.
So this is just falling?
The support,
Mm-hmm.
there's going to be an X and a Y.
Okay. Riley, I'm missing something.
Moment.
There we go. Fixed support, right? So it provides a moment reaction as well. Okay. Oh, nice. 14 minutes left. Let's solve this problem. I think it's more fun if I have one person solve the whole thing. Who wants to be that volunteer? Not you two. Who wants to be the volunteer? Tyler, you need the practice. Go ahead.
Okay. Alright,
Feel free to help everyone, okay? If you know that he's in the wrong path, help him. Don't let him make a fool out of himself. Go ahead. You can do it. You can do it. Tell me what to do.
We'll start with our unknown equations.
Okay?
So f of x, so f of x equals 0,
Mm-hmm.
and that would be r of x equals 0. And we can just go ahead and do the same thing for a moment. Wait. Okay. Let's just go to f of x. So someone f of x equals 0, f of y. Oh my goodness.
No, you're good. You're good. You're good. You're on the good path right now. You're on the right path.
God, forgive me, I'm kind of tired.
No, don't worry about it. We're all tired.
So, f of y, so 225 pounds, positive. We can do it negative. Minus 450 pounds. Plus ry equals 0. And ry equals 675 pounds.
Good. You did a good job. I don't want to embarrass you. I'm kidding. I want to embarrass you. Can we just give Tyler a hand? Chris? Yes? Have a question?
I just wanted to ask, just make sure, this is the part you added, right? Like technically from the original problem, this wouldn't be.
Yeah.
Because it's fixed, right?
Yeah, the original problem is just this.
Okay, so if it's fixed, we don't have that already. The,
No, it's fixed, and because it's fixed, we
okay,
have
yeah,
these
yeah,
reactions.
okay.
All right. What I'm saying, I didn't change anything in the system. I'm just adding steps to the problem. Okay, that's all I'm doing. Other Chris, let's wrap this up.
Okay, we'll do the sum of the moment equals 0. So it'd be
Which point do you want to take your moments about?
the original one that we already have. Okay, so the first one would be negative 225 pounds times 3 feet. Then minus 450 pounds times 4.5 feet. And then
Leslie, what am I missing?
The moment of pause and
There we go. Can we solve for this, MR? Thank you, Chris. Again, let's embarrass our friend. Finally, we can solve for this MR. And let's see, I need one final person to embarrass today. Lorenzo, would you please give us our answer? But before you do that, would you please stand up?
Yeah, oh yeah.
And everybody just stare at him directly.
2,700 pound feet.
Thank you. Lorenzo, would you like for people to clap for you?
Doesn't matter.
All right, then don't clap for him. Don't give him the satisfaction. Okay, so how we solve this system? Right? We did. We found all of our forces. We found all of our reactions. Ergo, we have solved this system. I'm glad you brought the question up. I think it was Hunter, right? Because now we know. Sometimes it's best to split up our loads into things that we can solve. Okay? So if a trapezoid, we split it up into a triangle and a rectangle. Any questions at this point? Why are we putting our things away? Is it time to go? Not yet. Okay. We got 9 more minutes. Do you think we can do one more problem in 9 minutes? I think we can. And I think the more problems we do, the better, because the better prepared we'll be. Trying to find one that's, a little bit more work. These problems are actually all kind of easy, but it's okay. All right, let's do an easy one, because we're going to have about 5 minutes to solve it anyway, so let's just pick an easy problem. How do you feel with this material? Do you think it's manageable? I think it is. Sometimes we may need a little bit more practice, but I think this material is very manageable. And this is pretty much all that statics is. I mean, we're going to start adding some things here and there, but this is statics, okay? So hopefully you'll realize why this class is not really that complicated. 5.9. Let me get a different marker. Let's see, we have a rigid body. I'm not even going to try to describe what this is. It's just a rigid body connected to a hinge and a wheel. What type of support does a wheel give you? What type of support is this wheel?
Roller.
A roller. Good. I like that the book draws supports in different ways, because it does allow us to, have a little bit of practice identifying different supports and their reactions. Okay, this is my system. Neglect the weight. We have a force of 750 pounds acting on it. What are the reactions in the system? In other words, I would like for you to solve the system. Now, I don't want to go over time, so if it is time to go, or if we're like a minute away, let me know so that we can wrap it up. But for now, let's just go ahead and draw a free body diagram. I think this is good enough for a free body diagram. We have our free body diagram. Actually, no, I'll draw it myself. And we need the forces acting on the system. What are those forces, Will?
What is it, hinge?
Okay.
There's an R, A, X, and then R, A, Y.
I'm choosing these directions arbitrarily. You can choose whatever directions you want. Okay, I'm just choosing these two arbitrarily because I know that that's going to be the answer. But anyway, you choose whatever direction you want. What else? What else? What else?
R 750 pounds. And then the distance from each side.
And the RB.
Okay. Okay, let's solve this problem.
So on the X is going to be REX and RBX, negative RBX.
What's RBX? Remember, let's try to write it in terms of
RB times cosine 30.
all this equals?
0.
Okay, two unknowns. Next.
In our Y, we're going to have RAY, RB sine 30, and negative 750.
All this equals?
0.
Two unknowns. And these two unknowns are actually, well, we have three unknowns right now total. RB, RAX, RAY. Three unknowns, two equations. Can we solve this? Okay, so what's next? Okay, so moments equals 0. And where do you want to take your moment? What? A? Okay. So moments at A equals 0. Got 3 more minutes. Can we finish this in 3 minutes?
750 pounds times 3 feet.
Positive or negative?
Negative.
Negative, okay.
We're going to have
RB plus RB sine 30.
and RB cosine.
RB sine 30 at what distance?
Times
6 feet.
What else?
RB cosine 30 at 2 feet.
Positive or negative? Good. All this equals? How many unknowns? Can we solve for it? I like your enthusiasm. Okay, let's go ahead and solve it. We get RB equals what? Let's see, 750 pounds times 3 feet divided by 6 feet times sine 30 minus 2 feet cosine 30. You may want to check that, double check that math. I'm not sure if I'm doing this right. I think I am. RB equals what? Yeah, I think it's right. We got 2 minutes. I thought, wow, we got 2 minutes. RB equals what? I hear those calculators clicking, so that makes me happy. But give me an answer.
1774.
1774? Is that what you said?
Yeah,
Okay.
that's right.
What are my units?
Pounds.
pounds. Okay. At foot, right? This is foot minus foot is just foot. These cancel out with foot. Okay.
So then we know our x, because we can plug in our 1774 into our x problem.
Before we move on, let's make sure that that's actually correct. So we get that RB equals 1774.
It's actually 5, I forgot to round,
But I'm getting a different number here, and I want to know why.
Did we set up the problem wrong?
I doubt it, right? We got our RB. Let's see, we have our summer moments.
is there a chance we flip the 6 and the 2?
We have a negative moment of 750 at a distance of 3 feet, right? We have a positive RB moment at a distance of 6 feet. Okay, that's RB, sine of.
30.
Now, is that right? Is it sine of 30?
It's going to be 60, isn't it?
I don't know. Let's see.
No?
We got our force in this direction. This is 30 degrees.
That's 30.
This is 30 degrees. What is this angle?
60.
60 degrees. Who gave me this angle as 30?
I did.
You did. Ooh, Hunter. All right. Let's make sure we get this right. We were so close to getting this problem correct until Hunter messed it up.
I went the vertical angles, but it's not.
Yeah.
536.
Thank you. 536 pounds. And now we get that RAY plus 536 pounds sine 60 minus 750 equals 0. Can we solve for RAY? Yes. RAX minus 536 pounds cosine 60 equals 0. Can we solve for RAX? Yes. This one's easy, right? What's RAX?
464. Oh.
Cosine 60, right? It should be half of this number, okay? Anyway, I think it's time to go. I'll let you get the answers yourselves, but the final answer should be 268 in the x direction, 286 in the y direction. Try to solve it. If you can't, let me know before the exam. If you can, let me know so I can make the exam harder, okay? Have fun. I will see you next week. Do your homework.